a simple alkene, then we'll practice it again with a more complex alkene. We're going to go to ethylene as our simplest possible alkene. And we're going to use this reagent called borane. We can notice that it has six electrons. It's violating the octet rule. This is an example of an empty p orbital, just like BF3 or aluminum trichloride, which we've worked with a little bit since I joined you this semester. We know that this is a Lewis acid using the empty orbital case. It wants 2 electrons. So it's an electron pair acceptor for sure, without a doubt. Our base in all these acid-base reactions we've been doing is the pi bond. It's been breaking and going to a multitude of different types of reagents. The most important one we did was H plus or HCl. This really illustrates whether this is a base and this goes to something that wants electrons. Well, here, this thing wants electrons. And sadly for us, the second we do this reaction, let's actually draw for a moment what actually happens in this particular stage. We're going to draw it in brackets. It's going to mean that this is a very, very brief-lived or short-lived reactive intermediate. That's what that one red arrow means. There's going to be some formal charges on some atoms here. Draw on where you think there are formal charges. You should put in 1 plus somewhere and 1 minus sign somewhere. Okay? So carefully catch up. I know that you're working hard to keep on track and keep up with the notes. I'm trying to pause and write at a real pace that I think you could keep up with. But there should be a plus charge and a minus charge on these atoms. Boron was neutral. We're giving it 2 extra electrons. Well, if we count up the valency of boron here, boron wants 3 in its valency, it has 4. Minus. Carbon, we've seen carbocations, and carbon is short an electron, so it should be plus. And what happens at this particular stage is immediately boron takes this hydride, which is nucleophilic. It likes forming bonds. You wouldn't know that unless I told you it. But boron, with a negative charge on it, this species becomes very active, becomes liberated, and it adds immediately to our alkene. And these two things have gone on from the same side by syn addition. This molecule, however, can freely rotate, so we don't see that, but this hydrogen, at least instantaneously, is inserted on the same side as this boron. Well, it would be lovely if this reaction was done, but it's not done. Boron has 2 more hydrides on it. And what boron does, it's a little bit pesky, especially for all of us. Boron can do this reaction 2 more times. What I mean by that is, if boron finds another alkene, boron's violating the octet rule again. It can accept an electron pair from our alkene. It then satisfies the octet rule. It becomes negatively charged. A positive charge starts building up on carbon. Then boron immediately donates one of its hydrides back to carbon. So, for the time being, it looks like boron has done this cycle 2 times. So now we've added a second molecule of ethylene to boron. Kind of strange. It's going to go 1 more time. There's another hydride here. A lot of fun pen colors. I'll use black. Boron, violating the octet rule, happily helps break carbon-carbon pi bond. That would build up plus charge here. At the same time, negative charge is building up on boron. And boron takes this negative charge in the form of a hydride, and we end up putting 3 molecules of our alkene onto boron. First one is the blue one we put on. Second one is the red one. And finally here, we put on another molecule of alkene, and it takes the form of an alkane. This process happens 3 times, stops, and then it's treated with potassium hydroxide and permanganate. Potassium hydroxide and hydrogen peroxide, and we end up liberating 3 moles of alcohol. There's an extra hydrogen here and an OH here, and these came from this particular process. That's the net result. Originally this was an alkene. So we make 3 moles of this, and we make 1 mole of BOH3. This particular thing is not important. The key point is we're taking alkenes and making alcohols. The process is quite different than what we've seen before. It happens by syn addition, giving cis stereochemistry. And we're going to do another more complex substrate to help us see that the alcohol group goes to the less substituted side. We'll see that right now. We'll work through this example again slowly. This mechanism, you're required to know and understand all the details that I've included here. Last step, mechanism's not required. If you care about it, it's in the textbook, but I won't ask it of you. Let's do this again with a different substrate. We'll go more slowly this time, and I'm going to give you the opportunity in your notes that when you're recreating, repracticing these notes, you'll have a great problem that you can work on your own. I'm going to set it up for us. I'm going to get it started, and then I'm going to give you enough clues, enough suggestions, enough hints that you should be able to carry this one out on your own. Let's start this from the very beginning type of principle. We have an alkene. All right, let me fix this, sorry. And we're going to react with borane. So I just want to make this methyl cyclohexene molecule. This is the best substrate for us to use in our practice because it allows us to carefully keep track of stereochemistry and regiochemistry. This one has different carbocations. Here's a tertiary carbocation and a secondary position. So that's why I like this substrate so much. Now there's 2 possibilities. The first possibility is unavoidable. Boron is an electrophile, or it's just something that wants electrons. We did HCl, Br2, mercury, lots of things we've done. Pushing these electrons, doing this. Which side is boron going to preferably go to? Is it going to prefer to go at position 1, putting plus charge on position 2? Or is it going to prefer to go to position 2 and put plus charge on position 1? You should be able to answer that or predict that based on what we've learned so far. This rule stays the same. If this was H plus or HCl, where would you put H? Where would you put Cl? Well, we know that it's going to go to the less substituted side. Plus charge is going to build up on the more substituted side. And so what we're going to do with this mechanism is, all at once, and imagine this is coming in from the top side of this molecule. The alkene breaks to bond to boron. Negative charge builds up here, builds up onto the hydrogen. Plus charge builds up onto carbon. This carbon, carbon number 2. And it adds from the same side. So let's draw this really carefully. We'll draw our carbon framework and skeleton in blue. And I'm going to draw the newly added things in red. And they've added with syn addition. Notice how both groups that went on in this step went on with syn addition. What's the stereochemistry of these newly added things? Stereochemistry of these two groups is cis, if we're referring to this group and this group. Cis is a relative term. We could talk about this boron here and this methyl group here. Those would be trans to one another, but the things that I've added have gone on with cis stereochemistry. This process can repeat 2 times more if we add more alkene to it. Boron has another hydride available to it. This is an alkene. You should, on your own, practice this problem. Do the same thing again. This alkene attacks boron. There's 2 different positions here, 1 and 2. As the alkene attacks boron, plus charge starts building up on position 2. Minus charge starts building up on boron, and boron will immediately donate its hydride to the more substituted side. Mechanism step is here. It's already here, all the answers. You just need to do this again. If you do this one more time, you'll get to some species that has carbon group there, that's going to be the form of a ring. And we could do this another time. So these here are just kind of clues. So at the end, you're going to end up with boron here. And what I've drawn in blue here is the thing that I started from the beginning. But you need to do this mechanism again. Some clues are here. You're going to get to something here with 2 different R groups. You're going to do it again. You're going to get to something here with 3 identical R groups that are going to look like this, but I want you to practice the mechanism. Practice it here once, you'll get to something here. It should be drawn out with lots of wedges and dashes. When you get to this, there'll be 1 hydride left. Practice it again with this. How does the mechanism work? Well, this attacks boron. The hydride goes to the more substituted side. Boron's attached to the less substituted side. So this will be repeated 3 times. And if you actually take this compound, react it with hydroxide and hydrogen peroxide, and we didn't do this mechanism, it's not drawn in our notes, no way you should think you should have to know it. The final product we get here is an alcohol. Maybe a mnemonic for boron. See all these oxygens here? Lots of oxygen. This particular overall reaction produces alcohols. These 2 groups were installed from the same side. This is the result of syn addition. This is cis stereochemistry. And notice that the alcohol group is at the less substituted side of alkene. Okay, I'll leave this here for a minute, but this is really the culminating example, the most challenging one that we've looked at. It's different than all the other ones. Beginning is the same. Alkene attacks something that wants electrons, but right away donates hydride back. Boron goes to the less substituted side. That's normal. Putting plus charge here, then hydride went to the plus charge at the more substituted side. This particular structure, if we keep doing this 2 more times, these groups will be replaced with this. You'll have to practice drawing it. This is going to take a full sheet of paper to practice, so by all means get a fresh sheet of paper, try your best on this, show me your work tomorrow in office hours if you really want help with this problem. After this process repeats 2 more times, we're left with 3 replicates of this carbon framework at all 3 locations. If we oxidize this with hydroxide, hydrogen peroxide, it's just going to cut this boron bond and replace it with an OH group. If we look at this very, very carefully, compared to our starting alkene, both of these groups went in on the same side, and the alcohol ended up going to the less substituted side, not the more substituted side. This is called anti-Markovnikov also, if you see it. I don't care about that word. But you could try this reaction with mercuric acetate and water. You could try this reaction with H2SO4 and dilute water. Those two reactions would have the alcohol go on the other side, at the more substituted position. So this isn't particularly magic, it's just that we're adding water after we add boron, and boron's at the less substituted side. Boron's at the less substituted side, and there's chemical reagents that can swap this for an OH group. So all the rules are the same at the beginning. Alkene breaks, tacks this at the less substituted side, putting plus charge and more substituted side. And just at the last minute, since boron was installed first at the less substituted side, the OH group goes in that position. This is definitely challenging. I acknowledge that. This is the thing that's important for us to practice very carefully. I've developed these notes slowly and methodically today for us, pointing out points of contrast, points of similarity. Okay, and so this is the final example that you'll have to work through a mechanism on.